You know how it is, you're staring at some code and you just think, there's got to be a smoother way.
Oh, definitely.
And, well, more often than not, especially with Java 8, that little voice is absolutely right.
It really was a turning point, wasn't it? Java 8 brought this incredible efficiency and expressiveness to so many common coding tasks.
Yeah, the way we handle collections, process data, it just changed the game.
Absolutely. Streams, lambdas, optional. They opened up a whole new way of thinking about solutions that are often, cleaner and sometimes faster too.
Which brings us perfectly to today's deep dive.
Mm.
We've pulled together a really great set of explanations, code examples, all focused on tackling those typical interview questions using Java 8.
Right. The kind of things that always seem to pop up.
Exactly. So maybe you're prepping for an interview right now, or maybe you're just looking to, level up your Java skills, feel a bit more comfortable with streams.
Or maybe you just like seeing elegant code.
Yeah, that too. Either way, you're in the right place. We're aiming for quick but thorough insights. We'll cover finding duplicates, reversing linked lists.
Oh, the classic linked list reversal.
Yep. Plus stream stats, slicing streams, dealing with nulls using optional.
Which is huge.
Totally. And sorting, fetching top elements, short-circuiting, grouping with grouping bead, even some string manipulation stuff.
It's a good mix, and the sources cover quite a bit of ground.
For sure. So our mission today, let's really dig into these examples, pull out the most valuable techniques, the key insights, and basically make you feel way more knowledgeable and efficient with Java 8.
Sounds like a plan. These aren't just interview tricks either. Understanding these patterns makes your everyday code better, cleaner, more maintainable. We'll hit the how, but also the why, and importantly, the trade-offs.
Exactly. It's about understanding the choices. Okay, let's jump in. First up, finding duplicate elements in a stream. Seems simple, but it comes up all the time.
It really does. And the interesting thing is our sources show 3 different Java 8 ways to do it.
3.
Okay.
Yeah. Using a set, using Collectors.groupingBy with counting, and using Collections.frequency. Each has its own pros and cons.
All right, let's break down that first one. Using a set, this feels like classic data structure thinking, right? Choosing the right tool.
Absolutely. The core idea hinges on what a set fundamentally is.
Right.
It only holds unique items.
Right.
So the code streams the elements. For each one, it tries to add it to a hash set. Now, the key is the add method itself.
What about it?
It returns false if the element is already in the set.
Okay, so you filter based on that return value.
Exactly. The stream filter keeps only those elements where scene.addEn returns false.
I see that in the find duplicate names code.
Yeah.
That .filter_ns scene.addEn line. It's pretty concise. So false means I've seen this before, meaning it's a duplicate, so keep it.
Precisely. And then you collect those into a set just to get the unique duplicate names.
And the cool part is finding unique names uses almost the same logic, just flipped. Yeah, find unique names just uses .filter, scene.add. If add returns true, it's the first time seeing it, so it's unique at that point. Keep it.
That's really efficient, getting both duplicates and uniques so easily.
It is. And because hash set lookups are fast, often constant time on average, this method scales pretty well. It's a great example of how data structure choice impacts performance.
Definitely a slick approach. Okay, method 2, Collectors.groupingBy. This sounds a bit more involved.
It is, but wow, grouping by is like the Swiss Army knife of collectors. Super versatile.
How does it work for duplicates?
Okay, so first you group the stream elements using function.identity. Basically, group by the element itself.
Function.identity. That means use the thing itself as the key, right?
Exactly that. A simple function that just returns its input. So you get this temporary map where keys are the unique elements. Then the second part of grouping by comes in, collectors.counting.
And that just counts how many times each key appeared.
Yep. So now you have a map where keys are the elements and values are their frequencies in the original stream.
Okay, map of names to counts. Got it. Then how do you get just the duplicates?
You take the entry set of that map gives you pairs of name and count, stream those pairs, then you filter again.
Filter for counts greater than 1.
Exactly. Keep only entries where the value, the count, is 1. Then map those entries to get just the keys, the names that appeared more than once, and collect those into a set.
Makes sense.
Yeah.
A few more steps than the set method, but I can see how you'd use this if you needed the counts of all items, not just the duplicates.
Right. It's more flexible in that regard. Interviewers might ask about function.identity too, so it's good to know it's just that simple placeholder.
Good tip. Okay, method 3, Collections.frequency. This one feels more direct.
Intuitively, maybe, but it has a potential catch.
Okay.
The approach is simple. For each element in the stream, you call Collections.frequency, original list element.
And that just tells you how many times that element appears in the whole list.
Correct. If that count is greater than 1, you keep it as a duplicate.
But what's the catch?
Performance, especially on large lists. Think about it. For every single element in the stream, you might be iterating through the entire original list again inside that frequency call.
Ooh, yeah. That could be quadratic complexity, couldn't it? Lots of repeated work.
Potentially, yes. It can be significantly less efficient than the set or grouping by methods for large inputs.
So easy to understand the code, but maybe not the best choice performance-wise. Good to know that trade-off.
Definitely.
So the big picture for finding duplicates.
It's that Java 8 give you options. The set method is often very efficient. Grouping by is powerful and flexible, especially for full frequency maps. Collections.frequency is simple to read, but watch out for performance on big lists.
And in an interview, being able to discuss why you chose one over the other is key, right? Not just knowing one answer.
Exactly. Explaining the trade-offs, readability versus performance, flexibility shows deeper understanding.
Makes perfect sense. Okay, let's switch gears. Reversing a linked list. A bit of a detour from streams, but such a fundamental data structure problem.
Absolutely. And the linked list reverse example gives a nice, clear, iterative solution. It's all about manipulating those next pointers carefully.
Yeah, I always have to mentally trace the pointers on this one. Can you walk us through the reverse list method again?
Sure. You need 3 pointers, prev, current, and next.
Okay.
Prev starts as null. Current starts at the head of the list. Next also starts null just for initialization.
Got it.
Then you loop while current isn't null. Inside a loop first, you save current.next into the next variable. You need this so you don't lose the rest of the list when you change the pointer.
Right. Store the next step before you break the line.
Exactly. Then the core reversal, current.next is prev. You make the current node point backwards to the previous one.
Okay.
Then you advance your pointers, prev becomes current, and current becomes the next node you saved earlier.
So prev moves to where current was, and current moves to the next node in the original sequence.
Yep. You repeat this. Save next, reverse pointer, advance prev, advance current. It's like you're inching along the list, flipping each pointer as you go.
And when the loop finishes, current is null.
And prev is sitting at what used to be the last node, which is now the first node of the reverse list.
Yeah.
So you update the list's head to point to prev.
Okay. That makes sense. And the node's stressed using that separate current pointer. Why is that so crucial again?
It's your handle for iterating. If you just manipulated head directly while also changing its next pointer, you could easily break the chain and lose track of the rest of the list nodes. Current lets you safely step through, node by node, modifying pointers without losing the overall structure.
Right. Avoids accidentally orphaning the rest of the list. Definitely need to be careful there. Okay, back to Java 8 streams. Getting quick stats, min, max, average, sum, super common.
Totally. And the stream statistics example shows how easy Java 8 makes this. Got a list of numbers, like ages. Calculating stats is almost trivial.
Looks like summary statistics is the star here. How's that work?
First, you stream your list of numbers. Let's say it's a list integer. Now, for these numeric stats, you need a specialized numeric stream, like an int stream. So you use map to in, integer.int value, or map to long, or map to double if needed.
Right. You need to map to the primitive stream type to get those methods.
Exactly. Once you have that int stream, you call summary statistics. This single call does all the work.
And it returns.
It returns an IntSummaryStatistics object. Think of it as a little container holding all the results. The count, the sum, the minimum, the maximum, and the average.
Wow, all in one go. That's way better than looping and tracking 5 different variables yourself.
Much cleaner. And then you just call methods on that object. Get min, get this, get average, whatever you need.
Super efficient.
Yeah.
Okay, what if you don't need the whole stream, just a slice of it?
Yeah.
That's skip and limit, right?
That's them. They're intermediate operations for taking a subset. Skip in throws away the first n elements.
Okay.
And limit takes at most the next m elements after the skip.
The stream slicing example uses them to find the second and third youngest ages. How does that play out?
So, you stream the ages. Let's assume they're sorted youngest to oldest. First, skip 1.
Throws away the absolute youngest.
Right. Then, chain.limit 2.
Take the next 2.
Takes at most the next 2. These will be the second and third youngest. Then you collect those into a list.
So the order is crucial. Skip first, then limit.
Definitely. Skip past what you don't want, limit to what you do want from the remainder.
What if you try to skip more elements than the stream has?
No problem. You just get an empty stream.
And limiting more than what's left?
Also fine. You just get whatever elements are left. No errors.
Good to know. Okay, let's tackle something that prevents a lot of pain. Handling nulls with Java 8 optional.
Ah, yes. The bane of many developers. Null pointer exception. Optional is a fantastic tool for making the possibility of absence explicit.
It's basically a wrapper, right?
Right.
A box that might contain a value or maybe empty.
Exactly. It forces you to consciously think about and handle the what if it's not there case instead of getting a nasty surprise at runtime.
And the examples show a few key ways to work with it. First up, or else.
Or else, default value is your basic fallback. If the optional is empty, it just returns the default value you provide. Like in the example, or else anonymous returns anonymous if the name isn't found.
Super clean way to provide defaults. Next is or else throw, for when missing isn't okay.
Precisely. Or else throw, exception supplier, lets you specify exactly what exception should be thrown if the optional is empty. You provide a lambda that creates the exception, makes it very clear that absence is an error here.
Then there's if present, doing something only if the value exists.
Correct. If present consumer takes a lambda, a consumer that accepts the value. That lambda only runs if the optional actually holds a non-null value. If it's empty, nothing happens. It replaces that if value check.
Neat. And the last one, if doesn't else. Seems like it combines things.
It does. If present else, consumer runnable, takes 2 lambdas. The first runs if the value is present, like if present. The second, a runnable, taking no arguments, runs if the optional is empty. It's a direct if this, do that, otherwise do this other thing structure for optionals.
Very clear.
Yeah.
And the notes mention optional dot of null too. When's that used?
That's typically how you create an optional in the first place when you have a variable that might be null. Optional dot of nullable, some potentially null value, creates an optional containing the value if it's not null, or an empty. Optional if it is null. It's the safe way to wrap existing values.
Got it. Optional is just so valuable for robust code. Okay, shifting focus again. Sorting. Sorting a list of objects, say, employees by salary.
Classic requirement. The sort employees by salary example shows the Java 8 way. You stream the list, employees.stream. Then you use the sorted operation.
And sorted needs a comparator to know how to sort, right?
Exactly.
Yeah.
You pass a comparator that defines the comparison logic. The example uses a lambda for this. O1, O2, longest long.compare, O2.getSalary, O1.getSalary.
Okay, break down that lambda. It takes two employees, O1 and O2.
Right. And long.compare, value 1, value 2, compares two longs. The key here is the order of O2.getSalary and O1.getSalary.
Putting O2 first means higher salaries come before lower salaries, descending order.
Precisely. If you swap them to long.compare, O1.getSalary, O2.getSalary, you'd get ascending order.
Makes sense. And then you just collect collectors.toList to get the sorted list back.
Yep.
Now, building on that, how about getting just the top N highest paid employees?
Easy peasy once you have the sorting. The top N salaried employees example shows you just add .limit N after the sorted call.
So sort descending by salary, then .limit 3 gives you the top 3.
Exactly. Limit just takes the first N elements from the already sorted stream.
And that example also showed a cleaner way to make the comparator.
Ah, yes. Instead of the full lambda, you can use comparator.comparingLong employee.getSalary.reversed.
How does that work?
Comparator.comparingLong takes a function that extracts a long key, here, employee.getSalary. It creates a comparator that sorts by that key in natural ascending order.
Okay.
Then you just chain reversed onto that comparator to flip the order to descending. It's often seen as more readable.
Yeah, comparing long with a method reference in reversed definitely reads nicely.
Yeah.
Okay, slightly trickier. Getting employees with salaries less than the nth highest salary.
Right, the employees below nth highest salary example. This takes a couple of steps.
Okay,
First, you still need to sort all employees by salary, descending, get that sorted list.
like before.
Then you need to find the salary of the nth highest paid person. That's the employee at index N1 in your sorted list.
Assuming zero-based indexing. And need to check if the list even has N employees first.
Crucial check, yes. Avoid that index out of bounds exception once you have that nth salary value.
Then you go back to the original list.
Yep, stream the original list and filter it, keeping only employees whose salary is strictly less than that nth salary you found.
Okay, so it's a two-pass approach. Sort to find the threshold, then filter based on the threshold.
Exactly. It combines sorting and filtering to achieve that specific goal. And that check for list size is important practical detail.
Definitely. Okay, let's talk optimization. Short-circuit operations in streams. Making things faster.
Yes, potentially much faster. Short-circuiting means the stream pipeline can stop processing elements early as soon as the final result is determined.
Like Boolean and end-in, or where you don't evaluate the second part if the first part decides the outcome.
Exactly the same principle. It avoids doing unnecessary work, which is huge for large or even infinite streams.
The notes mentioned intermediate and terminal short-circuit ops. Limit is an intermediate one.
It is. Limit n tells the stream it only needs n elements. Once n elements have passed through the limit operation, the upstream operations can stop. If you have filter.limit5, the filtering can stop once 5 elements pass the filter. No need to filter the rest of the stream.
Makes total sense. Saves computation. What about terminal short-circuit operations?
Several key ones. Find first, find any, all match, and none match.
Okay, find first.
Returns an optional with the first element it sees, stops immediately after finding one.
Of I and E.
Similar, returns an optional with an element, but not necessarily the first, can be faster in parallel streams because it takes the first one found by any thread.
Got it. And the matching ones? Any match predicate.
Returns true as soon as it finds any element matching the predicate. Stops right there.
All match predicate.
Returns true only if all elements match. But it can return false and stop as soon as it finds the first element that doesn't match.
Okay. And none match predicate.
Returns true only if no elements match. It stops and returns false as soon as it finds the first element that does match.
So all of them are optimized to stop as early as possible. Really important for performance. Cool. Now let's dive deep into Collectors.groupingBy. You called it a Swiss Army knife earlier.
It really is. It's a terminal collector for organizing stream elements into a map.
The basic version just takes one argument.
Right, a classification function. This function determines the key for the map. GroupingBy then puts all stream elements that produce the same key into a list associated with that key in the resulting map.
The example grouped employee with age objects by age, so the code looks like.
Employees.stream.collect, collectors.groupingBy, employee with age.get.
And the result is a map integer. List employee with age. Keys are ages. Values are lists of employees with that age.
Exactly. Super useful for categorization.
But what if you don't want a list as the value, like maybe a set to automatically handle duplicates within an age group?
Good question. That's where the multi-argument grouping by comes in. The 2-argument version lets you specify a downstream collector.
A downstream collector.
Yeah. It tells grouping by how to collect the elements that fall into each group. So instead of the default collectors.toList, you can provide collectors.toSet.
So grouping by employee.getAge, collectors.toSet, would give a map integer set employee with age.
Precisely. Assuming your employee with age has proper equals and hashcode methods, the set will ensure uniqueness within each age group.
Very flexible. And the notes mentioned a 3-argument version too, for sorting the map.
Right. The 3-argument version is grouping by classifier, map factory, downstream.
Okay, classifier is the key, like age. Downstream is how to collect the values, like to list or to set. What's map factory?
It's a supplier that creates the actual map instance you want to use. So if you want the final map to be sorted by keys, the ages.
You supply a tree map.
Exactly. You use treemap.new as the second argument. So grouping by employee.getAge, treemap.new, collectors.toList gives you a map sorted by age where each age maps to a list of employees.
Wow. Okay, grouping by is seriously powerful. Classifier, map type, value collection type, total control.
It really covers a lot of common data aggregation patterns very concisely.
Let's look at some practical text examples now, counting word occurrences in a string.
Classic text processing. Java 8 makes it really elegant with grouping by and counting.
The word count example.
Yeah.
How does it work?
First, split the string into words. Input strings.split is common, splitting on white space. That gives an array of words. Then, stream that array, arrays.stream. Words.
And then collect.
Yep, collect. Collectors.groupingBy, word, collectors.counting.
So group by the word itself. Word is the identity function again.
Right.
And the downstream collector is collectors.counting, which just counts how many items fall into each group.
Exactly. Result, map string, long mapping each unique word to its frequency. Way cleaner than manual iteration with a hash map.
Definitely. Okay, similar idea. Finding duplicate characters in a string.
The duplicate characters example handles this. Slightly different start because a string isn't directly streamable objects.
How do you stream characters?
Use the chars method on the string, .cr.chars. This gives an in-stream of the character code points.
An in-stream, not characters.
Right. So the next step is map to objc, .char, to convert those integer code points back into actual character objects. Now you have a stream character.
Okay, stream of characters. Then it's like the word count.
Pretty much. Collectors.groupingBy, CCC, collectors.counting. Group by character count occurrences. Gives you map character, long.
Map of characters to their counts.
Huh.
And to get just the duplicates.
Filter the map's entry set again. Filter entry.getValue1. Keep pairs where the count is more than 1.
They get the keys.
Map back to the keys, the characters themselves, using map.entry.getKey, and collect into a set character to get the unique duplicate characters.
So even for characters, the stream pipeline with grouping by and filtering works nicely. It's all about getting the data into a stream first.
Absolutely. Once it's a stream, you have all these powerful tools like collectors and intermediate operations at your disposal. These examples really show off how much Java 8 can simplify common problems.
Well, this has been quite the deep dive. We covered a lot of finding duplicates, reversing lists, stats, slicing, optional.
Sorting, grouping, short-circuiting.
Yeah, a wide range.
And the key takeaway seems to be that Java 8 offers these elegant, often more efficient, and definitely more readable solutions for these common tasks. For sure. And like we said, it's not just about interviews. These techniques genuinely make everyday coding better, cleaner, more maintainable code. That's a huge win.
Yeah, definitely. So thinking about all these powerful features, it kind of makes you wonder, doesn't it? What other common programming tasks, things we do all the time, could we tackle with this kind of Java 8 clarity and efficiency?
That's a great question.
That's something to mull over, perhaps? Maybe even look back at some older code with fresh eyes. Anyway, thanks so much for walking through all this with me.
My pleasure. It was a good discussion.